Hi folks, welcome to the Concept Roundup for sections 4.1, 4.2, 4.4 for Math 611B. We're looking at chain rule, implicit differentiation, and derivatives of exponential and logarithmic functions, as well as logarithmic differentiation as a technique. The only thing from chapter 4 that's missing here is 4.3, which is inverse trig functions, and we'll deal with that in a separate video. Down below, you'll find that the video is time-stamped, so if you're interested in, say, implicit differentiation, just look at where that starts and click. There's also a PDF of the blank notes, so if you want to print off and work along, you're welcome to, and also a PDF of a review sheet with some worked solutions. As usual, this is not an exhaustive look at these concepts, but it's kind of a look at the main ideas. So let's dive in. Chain rule. Here's the big idea if we state it informally. When you have a composite function, that means a function with an inner part and an outer part. The derivative is going to be the derivative of that outer times the derivative of that inner part. So what that means is we have to look at a function and get some sort of intuitive idea of what's meant by outer and inner. So if I have this function here, y equals sine of 3x squared minus 2x plus 1. When I look at that, I think if I were to put a number in it, first I would have to do this, 3x squared minus 2x plus 1. If I put, say, the number 1, I'd have to square the number, times it by 3, subtract 2 times the number, and add 1. So that's the inner, is the polynomial. The outer thing is what's happening to that polynomial. Namely, it's having sine applied to it. So when I differentiate, here's what I get. dy by dx is derivative of the outer. So the derivative of sine, we know, is cosine. And I change nothing with what we're taking the cosine of. It's 3x squared minus 2x plus 1. Now we're going to multiply it by the derivative of the inner, which would be 6x minus 2. Okay, that's the derivative of 3x squared minus 2x plus 1. So again, derivative of sine gave us the cosine. Derivative of 3x squared minus 2x plus 1, or the inner, gave us that 6x minus 2. If we rewrite this, maybe we'll want to put the 6x minus 2 out front. And there we go. There's the expression for the derivative of that original function, that composite function. If we want to do it formally, here's the way we would. So often we prefer to do these informally. But we can also use formal substitution. And so here's the way it reads. The derivative with respect to x is the derivative with respect to u, that's kind of the outer part, times the derivative of u with respect to x. Okay, now when you read that, it doesn't make a whole lot of sense. But here's the trick. U is the inner part. Okay, so if we use formal substitution to do the one we just did, we already set it up and said the inner part was 3x squared minus 2x plus 1. So we'll say let u equal 3x squared minus 2x plus 1. That is the inner part of this function. And we're going to get the same result. We're just going to do it formally. The derivative, well, du by dx, it's just the derivative of that. So it'll be 6x minus 2. And here are the steps to do this formally. Number 1, we're going to substitute. So to start with, we had y equals sine of 3x squared minus 2x plus 1. But we're saying u is this thing here. So I can call this y equals sine of, instead of 3x squared minus 2x plus 1, sine of u. The next step would be to differentiate. And here's what the chain rule is saying. The derivative with respect to x is going to be the derivative of sine u, so that's cos u. And then you have to tack on this du by dx. Step 3 would be to sub back. So notice the differentiation was really easy. Sine u became cos u. You just needed this du by dx on the end. And when we say sub back, we mean rewrite it in terms of x. So instead of writing cos u, we know that u is 3x squared minus 2x plus 1. Okay? That deals with this part right there. Now, we'll multiply it by du by dx, which we said was 6x minus 2. So I'm just substituting back in so that I'm working in terms of x's instead of u's. And when we're done, what do we get? 6x minus 2 by cos of 3x squared minus 2x plus 1. Now, let's take a look at the last slide. We got the exact same result with the exact same question. And that's good. We should get the same result. So, which one is more important? It's more important to know the informal way. But there are times when it's going to be good to be able to use a substitution, particularly later on in the course. So if you look at this and this doesn't make as much sense as the other way, that's fine. We want to do it informally as much as possible. So I put up here, wow, that was needlessly cumbersome. However, there will be times when substitution comes in handy, particularly when we begin integration later on. Okay, let's just try a few. I'm going to differentiate with respect to x. I've got y equals root of 1 minus 2x. And by now, we know that we want to write these as a power of a half. And when I see that, I need to make some decisions. What is the inner thing that is happening here? The inner is the 1 minus 2x. The outer thing that is happening in that function would be power of a half. Okay, so when we differentiate, here's what we'll do. We'll deal with the power of the half first, the derivative of the outer. So power comes down front, and power decreases by 1. So 1/2 goes down to negative a half. That's dealing with this sort of outer part. Now we have to multiply it by the derivative of the inner. And that would be 1 becomes a 0, minus 2x becomes negative 2. And from there, we can simplify it if we like. Okay, so we can write it in a prettier form. You might notice here that 2 on the bottom, 2 on the top, those are gone. That negative a half, power of negative a half, means this gets sent to the bottom. So an equivalent expression for the final answer might be negative 1 over the square root of 1 minus 2x. But the important part here is that we applied the chain rule. Now, it turns out that things might have more than just an inner or an outer. They might have multiple shells. And that's okay. We just work our way inside. So over here, I've got y equals cos cubed of 2x squared minus 1. Sometimes people get confused about what this notation means. Here is what it means. That cosine is being cubed. So if you look at that, the innermost thing that is happening is the 2x squared minus 1. If you were to put a number into this, substitute it in, that's where you'd start. And then after you've done that, you would apply the cosine. Maybe I should color code this a little better. So here we'll call this middle, would be cosine. And after you've done a bunch, you probably won't write this inner, middle, outer business. And the outermost thing that's happening is this power of 3. So cubing. And here's how we differentiate. I'm going to need a little extra space here. dy by dx is going to come from dealing with the outermost. So power of 3, 3 comes down front. Everything else stays the same. And now we've got a power of 2. The next thing I deal with is the cosine. So cosine, we know, becomes negative sine. So I'll have negative sine, and I don't deal with anything that's more sort of inward than the cosine part. So we still have 2x squared minus 1. And finally, we need the derivative of 2x squared minus 1, which we know is 4x. Okay, so there's something that has multiple shells. And now we're just going to simplify it. So in terms of monomials, we have a 3, we have a 4, we have a negative, and we have an x. So that makes negative 12x. This means cos squared of 2x squared minus 1. And also we have a sine of 2x squared minus 1. Let's look at one more in terms of basic chain rule stuff. So over here we have y equals x squared by the cos squared of 2x squared minus 1. What you want to watch out for here is the fact that you have functions of x multiplied together. That one and this whole thing. That's a product rule. Okay. And how we differentiate product rule is we say dy by dx is u prime v plus uv prime, okay, where u is the first part of the function. So here this would be u is x squared, and u prime would be 2x. V would be everything else, which is a big mess. 2x squared minus 1. And mercifully, we just did this derivative. That is, the v is what we did in part b. So we now know that its derivative is negative 12x cos squared of 2x squared minus 1 by sine of 2x squared minus 1. Now that looks like it's going to be horrible, but we still just substitute it into this. Okay, our product rule. So this is a product rule. Okay, let's see what that gives us. dy by dx is going to be u prime times v, which is cos cubed of 2x squared minus 1, plus u times v prime, negative 12x cos squared, 2x squared minus 1, sine of 2x squared minus 1. And from here, we're just simplifying, really. So we'll get dy by dx is 2x cos cubed of 2x squared minus 1, if we multiply everything else out, minus 12x cubed cos squared 2x squared minus 1 sine of 2x squared minus 1. If we decided that we wanted to factor it, we'd look for common factors. And those common factors would be 2, an x, and a cos squared. And that would leave us with, from this part, just cos of 2x squared minus 1. And from the other part, it would leave us with minus 6x squared sine of 2x squared minus 1. Okay. And either of these are right. We can write this or we can write that. It just depends on whether we want it factored or not. Okay, so that's the basics of chain rule. Now let's move on to implicit differentiation. Implicit differentiation is useful because it allows us to differentiate relations as they sit. And that means we can differentiate non-functions, or relations where y can't be isolated. That's kind of a simple way to define what a function is. It's one where we can write it in y equals form with no fancy business, like pluses or minus. In these examples, we'll always differentiate with respect to x. And here's the steps. Number 1, we'll differentiate. Number 2, we'll treat y as a function of x, which means the chain rule. What that means when you actually do this is that every time you differentiate something involving y, you tack on a dy by dx. Well, we're going to be lazy and use y prime, just so that we don't have too many fractions flying around. But really, if we want to be super duper clear, dy by dx would be ideal. And finally, we'll have to isolate y prime. So let's try a couple of these. We've got x squared plus y squared equals 1. That is the unit circle. So almost everywhere on the unit circle, things should be differentiable. We should be able to find the slope at any point, with the exception of right here and right here, because it would be vertical. Here's what the differentiation looks like. So we differentiate x squared, no problem, 2x. Y squared looks like this. It would be 2y and then times y prime. Okay, that's the tacking on a dy by dx or y prime. And then equals, well, the derivative of 1 is just 0. Okay, let's isolate y prime. So I'm going to have 2y by y prime equals negative 2x. I just moved that 2x over. I'm going to divide by 2y. And now what I have is an expression for the slope anywhere on that unit circle. And there are only certain numbers that you could put into it. And notice that the final expression has both an x and a y in it. And that tends to happen when you don't have a function to begin with. Okay, so there we go. There's our y prime, or our slope function. Okay, the next one, we'll try the same thing. Here's the pro tip. When we see here x and y in a quotient, we want to try to rewrite. Quotient rule with two variables, and then later on trying to isolate y prime, tends to be unpleasant. So what could we do to get rid of that fraction? We could multiply both sides by x. So multiply by x, and we're going to get x squared cos y equals y. And that's not so bad. We've got a product rule here. So if I were to write all the steps, I'd say u is x squared, u prime is 2x. V is cos y. V prime is going to be negative sine y. But I just differentiated something involving a y, so I need to tack on that y prime. And all that work is just getting it set up for the quotient, or for the product rule, rather. Okay, so we're going to have u prime v plus u times v prime equals the derivative of y, which would be 1 times y prime. Now notice we've got multiple terms that have y prime in them. So first of all, let's just clean up here. This is 2x cos y minus x squared sine y times y prime equals y prime. The way we deal with having multiple y prime terms is we combine them on one side. So I'll have 2x cos y equals y prime, and I'm going to move that other term over. X squared sine y times y prime. And then, notice there's a common factor of y prime. That's how we get the y prime on its own. So I'll have 2x cos y equals common factor of y prime, leaves us with 1, plus x squared sine y. And to finish it off, to get y prime on its own, I just need to divide by this on both sides. 1 plus x squared sine y. So in the end, our expression for slope is 2x cos y all over 1 plus x squared sine y. Now, just to illustrate that this is still telling us the same stuff that derivatives always have, let's do kind of a standard type of question where we're looking for the equation of the tangent. But what we're doing it on is a weird kind of relation. We have x plus cos y equals y. And here's what that looks like, this squiggly shape here. It contains the point, negative 1, 0. Okay. And what we want to find out is, what does it look like there? What is its slope going to be? I'm not quite sure. By this point, we know all we need to find out to get the equation of a tangent is the point and the slope. So in this case, we have the point we're dealing with. If we want the slope, we need to differentiate. So the derivative of x is 1. Derivative of cos y would be negative sine y, and we know that that gets multiplied by y prime because it's a derivative of y. Equals derivative of y, that's y prime. In other words, it's 1 minus sine y by y prime equals y prime. So again, we collect our y prime terms on one side. We treat y prime as a common factor. And we isolate y prime. 1 plus sine y. And now we substitute our point. So we're going to sub negative 1, 0. Now it turns out in this particular one, there's no x's at all. All I need to do is sub in the right y value. So if there were x's, I'd put in negative 1 for x. There's only a y here. So I'll put in 0 for that y value. Okay, and we're dealing in radians here. The sine of 0 is 0. So y prime is going to be 1 over 1, or 1. That's the slope of the tangent. If we want the equation of the tangent, well, here's our point-slope formula. And we just sub in. So it would be y minus 0. This is our y1 here. This is our x1. Equals m, which we found was 1. The slope is 1. X minus negative 1. Work that out. That gives us just x plus 1. I wonder if that looks right on the graph. If I go and type in y equals x plus 1, will that give us the tangent at the point negative 1, 0? Boom, sure looks like it. Okay, so we have found the exact same thing we've been able to find before, but in some slightly trickier expressions. Okay, now in class we took some time to prove the derivatives of e to the x and a to the x. Here we're just giving them. So if you have e to the x, the derivative is e to the x. That's pretty straightforward. A to the x becomes ln a times a to the x. So if you have a base other than e, then that's what you'll use. And in fact, it'll work for e as well, because ln e is just 1. As always, the chain rule applies. So from here on in, you really need to be looking for the chain rule all the time. If there's a composite, something with an inner and outer, you need to deal with them both. Okay, so right here we have y equals e to the 3x. That means its derivative is going to be stay the same. E to the x becomes e to the x, so e to the 3x will become e to the 3x. But we also have to multiply by the derivative of that inner part, the derivative of 3x. So it'll be e to the 3x times 3, or by the time we're done, 3 e to the 3x. If we try one that has a different base, we've got 6 to the power of 3x. We're using this rule here. All the properties stay the same. We just need a ln 6 out front, or natural log of 6. Okay, so to deal with that 6, we have a ln 6. Then 6 to the 3x. And then from the chain rule, you need the derivative of that 3x, which is 3. So by the time we're done, the derivative is 3 ln 6 times 6 to the power of 3x. These can be combined with quotient or product rule. Here we've got a quotient rule. So to set it up, I would figure out what the derivative of the top is. And here's how it works. Everything stays the same times the derivative of that power, which would be 2x. In other words, u prime is 2x e to the x squared plus 1. Okay, the derivative of the bottom, well, that's pretty straightforward. Derivative of x is 1. So now when we go ahead and differentiate, remember the quotient rule, u prime v minus uv prime all over v squared. So u prime would be 2x e to the x squared plus 1 times v, which is just x, minus u, which is e to the x squared plus 1, times v prime, which is just 1, all over v squared. Let's clean it up a little bit. So that's 2x squared e to the x squared plus 1 minus e to the x squared plus 1 all over x squared. And you're probably thinking, oh my, look at that common factor on top. Wouldn't mind taking that out. So we will. Either this or this would be appropriate, but it is nice to see the factored form. Let's go ahead and do an application involving exponentials. So the population of Earth in billions T years after January 1st, 2012 is given by this expression. And this is roughly right. That's the rate at which population is increasing on planet Earth, about 1.13% per year. So if we interpret p when t is 20, that just means throw a 20 in for t. Okay. And we head to the calculator. And we go 7 times 1.0113 to the power of 20. And we get 8.76 roughly. That's what p equals. And p was the population. So what that means is after 20 years, which would mean January 1st, 2032, the population will be 8.76 billion, which is terrifying. Okay, now we're going to find and interpret dp by dt, the derivative. So first of all, let's find an expression for that derivative. And it would be 7 stays out front. That's a constant. Look, it's a base other than e. So we're going to need a ln of 1.0113. And then everything just stays the same. Now you might say, well, what about the chain rule? Okay, you can apply the chain rule, but the derivative of t is just 1. So you'd just be multiplying by 1 at the end. When t equals 20, we'd have this. dp by dt is going to be 7 ln 1.0113 times 1.0113 to the power of 20. Okay, let's see what that gives us. 7 times the ln of 1.0113 times 1.0113 to the power of 20. And I get 0.985. 0.0985 rather. Which means nothing unless we use our units. And that's where the Leibniz notation is great. P is population. It means billion people. And T is time in years. So, per year. The derivative's positive, so we're increasing. So what this is saying is that after 20 years, and again, that means January 1st, 2032, the population is increasing at a rate. Slope is a rate of change. So increasing because it's positive at a rate of 0.0985 billion people per year. Or you could write that as 98.5 million people per year. But the derivative has meaning, and the units give it that meaning. Billion people per year. Taking a look here at derivatives of logarithmic functions, if y is ln x, then y prime is 1 over x. And that only works if x is greater than 0, because you can't take the log of a negative or 0. This one, if we have a different base, log base a of x, here's what we get. 1 over ln a times x. And again, that only works if x is greater than 0. If you can't see that, here it is. Okay, so let's try this out. Chain rule is going to apply. And we also look for opportunities to use our log laws. And the more you use these, the easier the differentiation will be. And I'll show you that in a couple of examples here. So the very first one, we've got y equals ln 3x. dy by dx, therefore, is going to be 1 over 3x. Okay, just like this. And then from chain rule, times the derivative of the inner, times 3. Or dy by dx is 3 over 3x. And some people might go straight there. Or better yet, dy by dx is 1 over x. Now let me show you another way that you could have taken a look at this. Y equals ln of 3x could also be written this way. I'm not differentiating yet, but it could be ln 3 plus ln x. That is our addition or multiplication rule of logarithms. And if you do that, then the differentiation gets even easier. Derivative of ln 3 is going to be 0. Ln 3 is just a constant. Derivative of ln x apparently is 1 over x. So we get our answer of 1 over x that much faster. Okay? And I guess it's not super fast in this case, but the trickier they are, the more it will help you out to use those log laws. Let's try this next one. We'll do it without using log laws, and then we'll do it with. Okay, so dy by dx, this has a different base, so that's when we use this business. So we'll have 1 over ln 4 times 3x. And that will be multiplied by the derivative of the inner, which is 3. Again, some people might skip straight to this. That's 3 over ln 4 times 3x. And the 3's here will divide out. So we'll be left with 1 over ln 4 times x, or x ln 4. If we were to do this instead with our log laws, I wrote all the log laws just with base of e with natural logs, but it works for any base. So we could write this as log base 4 of 3 plus log base 4 of x. And our derivative is going to be, well, this one will be 0 because it's just a constant, plus 1 over ln 4 times x. So there's less simplification that needs to happen in the fraction. We get straight to 1 over ln 4 times x. Either one's good. When we have derivatives of logarithmics that have composites, we can build in the chain rule with this handy-dandy trick. If you have the ln of some function of x, what you end up with is f prime over f. And I have a beautiful song for this. It goes like this. If you have the derivative of ln of f of x, it's original on the bottom, derivative on the top. There we go. Deriv on the top, original on the bottom. Okay, so it's an awesome little ditty, and you can use it. Original on the bottom, derivative on the top. Let's try it in this one. We've got a log involving a composite. So there's an inner and an outer part. This is great. Original on the bottom. That means the original thing you're taking the log of. And then its derivative, which is 6x, derivative on the top, right up there. Okay, I'm not going to win any Grammys for singing, but it can help you differentiate these logs. Okay. The next one, again, the more we use log laws, the easier this is going to be. So you can do the original on the bottom, derivative on the top business here. Original on the bottom, derivative on the top. But it takes some doing to figure out what the derivative of 10 over x is. How about this, though? Use your log laws. This is ln 10 minus ln x. Super easy to differentiate. Derivative of ln 10 is 0. Derivative of ln x is 1 over x. For comparison, if we were to do it the other way, and I'm going to erase this in a second, we'd have to think of this as y equals ln of 10 times x to the negative 1. And then I'll put my original on the bottom, and its derivative, which would be minus 10x to the negative 2 on the top. And then I'd have to mess with things. 10 divided by 10. Those are gone. Okay. That x to the negative 2 really should live on the bottom. That x to the 1 should live on the top. This is negative. Same answer, but more painful. Better to use the log laws. Same thing in this next one. If you skip the log laws here, your derivative part is going to be a quotient rule. But if you use the log laws, this is straightforward. And for each of those, we can go original on the bottom, derivative on the top. So derivative of x would just be 1. Minus, okay, the next one, original on the bottom, derivative on the top. Becomes a whole lot easier. That's one of the gifts of logarithms, is that it changes some difficult operations into easy ones. It changes powers into multiplication. It changes multiplication into addition. And it changes division, like here, into subtraction, which is easier to deal with. We can only take the log of a positive value, so the domains of logarithmic functions, and therefore their derivatives, are typically restricted. So the domain of this thing here, we just look for what illegal thing in math we'd be watching out for. Whatever we're taking the log of has to be positive. So we could follow that inequality through. There's the domain of the original. Now if I differentiate this, I'm going to have original on the bottom, its derivative on the top. It looks like that one's okay for some other values. Maybe you could put in 1,000,000 into dy by dx, whereas you can't put in 1,000,000 into the original expression. That's silly. We can't talk about slope on the original when the original didn't exist. So all these restrictions on the domain of the original also applies to the derivative. So if I were to talk about the domain of the derivative, I would also have to say it is x less than 3 over 2. I can't put in a number bigger than 3 over 2 because I can't talk about the slope of a function where it doesn't exist. Okay, last part. Logarithmic differentiation. This is a technique that can make finding the derivatives of difficult products and quotients much easier. And maybe it won't look that way at first, but sometimes we can end up with really, really nasty expressions. It gives us a way around differentiating them, or a way to differentiate them. It can also make some other types that are impossible differentiable, that wouldn't be possible without this technique. So down in example 10, I have something that is just horrible. And then worse than that, I have something that looks like it's impossible. Let's look at how we can use logs to make these both doable. So the steps are take the natural log of each side. Then you're going to simplify using log laws. This is the most important part of the technique. Use all of the log laws that you can. Differentiate each side, and we're doing that implicitly. So you'll end up with y prime over y on the left-hand side, because the left-hand side will be ln y. When you differentiate that, it's original on the bottom, derivative on the top, y prime over y. You'll isolate y prime, and finally we'll rewrite in terms of x. And as we go through this process, you'll see that at play. So take the natural log of each side. I'll have ln y equals ln cube root of sine 3x by 5x minus 3 all over x squared plus 1. Next step is use some log laws. So I notice right away that between this part and this part, there's multiplication. I can split those apart. I can call it ln of, well, I'm going to call this 3x sine 3x to the power of a third. And then I can say plus ln of this whole business. So I used basically the product rule of logarithms there. Okay, now what can I do with this expression, with this power of 1/3? I can bring it down. And that is not differentiating. That is just a property of logarithms. Okay, powers can come down front. Over here, in this part, that's a quotient, so I can rewrite it as ln of 5x minus 3 minus ln of x squared plus 1. That takes us to the end of section 2. Simplify using the expression using log laws. Now we're going to differentiate each side. So on the left, I'm going to have original on the bottom, derivative on the top. Okay. That's just using implicit differentiation or chain rule. Now, this expression here should be really easy for me to differentiate. I have the 1/3 out front, and then I'm going to multiply it by original on the bottom, derivative on the top. And the derivative of sine 3x is going to be cos 3x times 3. Okay, that sine 3x is a composite itself. You have to deal with the sign, and then you have to deal with the 3x. Next one, original on the bottom, derivative on the top. Original on the bottom, derivative on the top. We're going to isolate y prime, so that's going to mean multiplying both sides by y. So we get y prime equals y times, now I might do a little bit of simplification here, 3 on top, 3 on bottom, those are gone. So I'd have cos 3x over sine 3x plus 5 over 5x minus 3 minus 2x over x squared plus 1. And very lastly, we have this in terms of y. We kind of want to rewrite that y, so we have only x's to deal with. And the very first step, the opening problem, it told us what y is. Y is the cube root of sine 3x times 5x minus 3 over x squared plus 1. So I'm going to rewrite that in place of y here. Cube root of sine 3x times 5x minus 3 all over x squared plus 1. Okay. That's just going in place where that y was. And then everything else will stay pretty much the same. I can rewrite cosine over sine as cotangent, so cotangent of 3x plus 5 over 5x minus 3 minus 2x over x squared plus 1. Now you might be saying, that does not look like it's saving me a lot of heartache. But if we were to do this the other way, you'd have a lot of simplification to do. You would have a quotient embedded in a product with all sorts of chain going on. The actual differentiation here is really easy. It's just original on the bottom, derivative on the top. Okay. So that helps us do a really nasty looking one. The other one that was there was y equals x to the x. This one we have no idea how to deal with. So I'll do the steps. First step was take the log of each side. And if you didn't simplify from here, if you didn't use log laws, then you wouldn't be any further ahead. Okay, because we put the x to the x on the bottom, but we'd have no idea still what the derivative of x to the x is. Okay, so now we'll use a log law. You can bring that power of x down. And from here, it's going to be easy to differentiate. This is a product rule. Okay, so u prime would be 1. V prime, sorry, not y, v prime would be 1 over x. And we're ready to go. The left-hand side, original on the bottom, derivative on the top, y prime over y. And that's what the left will always look like. Right-hand side would be 1 times ln x, that's u prime times v, plus u times v prime. And we'll just follow it through. I'm going to multiply by y so that I isolate y prime. So I'll end up with y prime equals y times ln x plus x over x, that's just 1. Or finally, y prime equals y, which was x to the x, times, I'm going to write this as 1 plus ln x, so that it's clear that it's only the x that is having the logarithm applied to it. So logarithmic differentiation gets you around those cases where you weren't quite sure how to deal with, say, a variable in both the base and the exponent. That gets us to the end of this video. I hope that it's been somewhat helpful. Again, you've got a review sheet that's in the description down below. And good luck with your assignment.